Have you ever noticed how sidewalks have small gaps between the concrete slabs? Or how bridges have special joints that look like giant metal teeth? These aren't design mistakes. They are there for a very important reason called thermal expansion. Almost everything around us, from a metal spoon to a giant skyscraper, gets a little bit bigger when it gets hot and a little bit smaller when it gets cold. This might not seem like a big deal, but in the world of engineering and science, even the tiniest change in size can cause massive problems. It can make parts not fit together, cause materials to bend and buckle, or even break things entirely. This natural tendency to expand and contract is a constant headache for people who build amazing things. Now, let's take this problem and send it into space. Imagine a satellite orbiting Earth. In direct sunlight, its surface can get incredibly hot, well over the boiling point of water. Then, just moments later, as it passes into Earth's shadow, the temperature can plummet to hundreds of degrees below freezing. These extreme temperature swings are huge, and they happen over and over again. If a satellite's parts, like its sensitive antennas or camera lenses, were made of regular materials, they would constantly expand and shrink. This would throw everything out of alignment, making it impossible to get clear pictures or send accurate signals back to us on Earth. The problem of thermal expansion becomes a mission-critical challenge in the harsh environment of space. This is why engineers and scientists are on a quest for something special, materials that don't change size, or change very little when the temperature goes wild. We call these low thermal expansion materials. Think of a super-precise telescope, like the James Webb Space Telescope. Its giant mirrors need to stay in the exact same shape, down to the width of a human hair, to capture light from distant galaxies. If the mirrors warped even slightly from the cold of space, the beautiful images of far-off stars would become a blurry mess. Having materials that are stable and predictable, no matter how hot or cold it gets, is the key to unlocking the next generation of advanced technology, both here on Earth and far beyond. The dream doesn't even stop there. What if we could design a material that does the opposite of what we expect? A material that actually shrinks when it gets hot and expands when it gets cold. This is called negative thermal expansion, and it's a kind of engineering superpower. By mixing a material that shrinks with one that expands, you could create a new composite material that has exactly zero thermal expansion. It would be perfectly stable, a rock in a sea of temperature changes. This level of control would allow us to build structures and devices with unprecedented precision and reliability, solving problems that have stumped engineers for decades and opening doors to inventions we can only begin to imagine today. For over 100 years, engineers have had a few tricks up their sleeves to deal with thermal expansion. One of the classic solutions is a special metal alloy called Invar. It's a mix of iron and nickel, and it's famous for having very low thermal expansion at room temperature. Because of this, it has been used in all sorts of precision instruments, from scientific measuring tools to the shadow masks inside old CRT television sets. For a long time, Invar was the go-to material when you needed something to hold its shape. It was a reliable and well-understood solution that helped build much of the technology we relied on throughout the 20th century. However, these traditional materials are a bit like old flip phones. They were great for their time, but they have some serious limitations. Invar, for example, only works its magic within a very narrow range of temperatures. If it gets too hot or too cold, it starts expanding and contracting just like any other metal, losing its special ability. Another group of materials used for thermal stability are ceramics. Think of the tiles on the bottom of the space shuttle. They are fantastic at handling high temperatures, but they have a major downside. They are very brittle. You can't bend or stretch them. If you put too much stress on them, they can crack or shatter, which is not what you want for a critical component. These old-school solutions are also not very adaptable. You can't really tune their properties. An engineer is stuck with the specific thermal expansion that Invar or a certain ceramic provides. What if you needed a material that expanded just a tiny bit? Or one that shrank just the right amount to cancel out the expansion of another part? With traditional materials, you are mostly out of luck. It's like having a toolbox with only one size of wrench. This lack of flexibility means that engineers often have to design around the material's flaws, adding extra weight, complexity, and cost to a project just to manage the effects of temperature changes. This is where the need for a new idea becomes crystal clear. We need materials that are not just stable, but are also strong, lightweight, and, most importantly, customizable. We need to move beyond simply finding materials with useful properties and start designing materials to have the exact properties we want. The limitations of the old guard, their narrow operating ranges, their brittleness, and their one-size-fits-all nature, have pushed scientists to think outside the box. They started to wonder, what if the property wasn't just about the stuff a material is made of, but also about how that stuff is arranged? This question paved the way for a revolutionary new class of materials. Get ready for a mind-bending idea: mechanical metamaterials. The meta part of the name means beyond, because these materials have properties that go beyond the natural materials they are made from. Their secret isn't a new chemical element or a magic ingredient. It's all about their structure. Imagine building with Legos. You can use the same simple plastic bricks to build a solid wall, a flexible chain, or a complex machine. The bricks are the same, but the way you arrange them, their architecture, changes everything. Mechanical metamaterials work the same way. By designing intricate, tiny internal structures, scientists can make a material behave in ways that seem impossible. So, how do you use structure to control thermal expansion? It's all about clever geometry. Imagine a structure made of two different materials that expand at different rates. You could design a tiny V-shaped rib where the more expansive material is on the inside and the less expansive one is on the outside. When this rib gets hot, the inside material expands more, forcing the V-shape to fold inward and become sharper. If you build a whole lattice of these tiny ribs, the entire structure will actually shrink as it heats up. This is how you achieve negative thermal expansion. We aren't breaking the laws of physics. We are just using them in a super smart way to make the overall structure do the opposite of its individual parts. The best part is that this property is tunable. By changing the angles of the ribs, the thickness of the materials, or the overall pattern, engineers can dial in the exact amount of thermal expansion they need. They can aim for a large negative expansion, a small negative expansion, or they can perfectly balance the expanding and shrinking effects to create a material with zero thermal expansion. This is a complete game changer. Instead of being stuck with the properties of a material, we can now design the property itself. This opens up a whole new world of possibilities for creating custom components for high-tech applications, like the mirrors for space telescopes or the support structures for sensitive satellites. This amazing control has applications far beyond just space. Think about ultra-precise machines used to manufacture computer chips. Even a tiny temperature change in the room can throw them off. Metamaterials could create a perfectly stable framework for these machines. In medicine, tiny sensors placed inside the body need to be stable and reliable. For the future of technology, consider flexible electronics. As phones and watches become bendable, we need circuits that won't crack or fail as they warm up from use. Metamaterials can be designed to be both flexible and thermally stable, paving the way for durable, next-generation wearable devices that can withstand the rigors of daily life. Where do the ideas for these incredible structures come from? Sometimes inspiration comes from ancient art. The Japanese art of paper folding, origami, is all about creating complex, three-dimensional shapes from a simple flat sheet. Scientists are using origami principles to design metamaterials that can fold and unfold in response to stimuli like heat. Imagine a flat sheet that automatically pops into a complex shape when it warms up. Other designers are looking at soft, active materials, like the muscles in our bodies, to create metamaterials that can change their shape and properties on command. By combining these smart structures with materials that respond to light, electricity, or magnetism, we can create truly dynamic and intelligent systems. So, how do we actually build these tiny, complicated structures? The answer is one of the most exciting technologies around three-dimensional printing, or as scientists call it, additive manufacturing. Three-dimensional printers build objects layer by tiny layer, which is the perfect way to create the intricate internal architectures that metamaterials require. With three-dimensional printing, we can move from designing these structures on a computer to holding a physical prototype in a matter of hours. This technology allows for incredible complexity and customization, making it possible to create unique, one-of-a-kind parts designed for very specific jobs. It's the key that unlocks our ability to manufacture these amazing materials on a large scale. As three-dimensional printing technology gets more advanced, we will be able to print with a wider range of materials, including metals, ceramics, and polymers, all at smaller and smaller scales. This means our metamaterials will become even more powerful and versatile. We could print a single component that is part solid, part lattice, with its thermal expansion properties changing from one area to another. This would allow us to create integrated, multifunctional devices that are lighter, stronger, and more efficient than anything we can build today. The future of manufacturing is not just about making things, but about printing fully functional systems with programmed properties. We are standing at the beginning of a materials revolution. For centuries, we were limited by the materials we could dig out of the ground. Now, with mechanical metamaterials, we are no longer just material users, we are becoming material designers. By controlling structure at the tiniest levels, we can craft materials that solve age-old engineering challenges, like thermal expansion, and open up entirely new frontiers in technology. From more stable satellites exploring the cosmos, to more reliable medical implants and revolutionary flexible gadgets. These shape-shifting superstars are going to help us build a smarter, more resilient, and more amazing future. The next big thing in science might not be what it's made of, but how it's made.